Okay, here we go with our first set of notes on our thermodynamics unit. This one's going to be thermochemistry, chapter 5, mostly talking about energy, what energy is, how we look at energy, and then some enthalpy, which you've actually been exposed to already, is mostly just as temperature, and end with discussions of calorimetry, so some of the ways that we calculate enthalpy of a chemical reaction. So energy, as I'm sure you know, is just the ability to do work or transfer heat. Right? So if it causes something to move, we consider it work. If it raises the temperature of something, we would call it heat. And there's kinetic energy, which is the energy of a position or energy of an object based on its motion, right? So the energy of motion, versus potential energy, which you've probably talked about in terms of position, like going back to that bicycle rider at the top of the hill would have more potential energy, but we're going to think more about chemical compositions, the amount of energy you could potentially have. And we mostly talk about this as electrostatic potential energy with this equation that you've seen before. When we talk about energy, a couple of different units we might use. Mostly we would use the joule, which is the standard unit of energy. Sometimes we still use the calorie, which is just 4.184 joules. This one's an important thing. How do we determine the system versus the surroundings? So whenever we're talking about these reactions, we're trying to figure out the energy or the enthalpy or whatever, we're always talking about the system. Right? And so the system is going to include the molecules that you actually want to study. So if we're looking at this here, this is what the actual system is. Right? The surroundings are everything else. So here would be the cylinder or the piston and all the air surrounding that. So it's really important to differentiate what is the surroundings and what are the system that you're actually looking at. Work is moving an object over some kind of distance. So work equals force times distance, something you're probably familiar with. And then energy can also be transferred as heat, like we just said. Heat flows from warmer objects to cooler objects, obviously. And energy can be converted as well. We can go from one type of energy to the other. So we have lots of potential up here as this cyclist is just hanging out at the top of the hill, but once they start going down, that energy gets converted, the potential energy gets converted into kinetic energy. So at the bottom of the hill, all the potential energy she had at the top of the hill is now kinetic energy. She's changed it all. So that basically sums up the first law of thermodynamics, that energy is neither created nor destroyed, which you guys pretty much knew, right? If the system is losing energy, then the surroundings would be gaining that energy. The energy is not going anywhere. It's not disappearing. It's just changing locations. So the total energy of the universe then is constant, right? If the system loses energy, it's being gained by the surroundings and vice versa. The internal energy of a system, which we're going to be talking a lot about, is the sum of all the kinetic and potential energies and everything going on with that system. So we just use the big letter E for that to mean the internal energy of the system that you're looking at. And so by definition, the change, the internal energy, is just the final minus the initial, which is pretty basic. So delta E, delta means change. Change in E is just the final energy minus initial energy. And so if you have a positive delta E, that means that the system absorbed energy from the surroundings, and we call that an endergonic reaction. So you've heard of endothermic before, like temperature going, or heat going in. The same thing. This is energy is being absorbed from the surroundings. And then conversely, if it's less than 0, so if you have a negative delta E, the system has released energy to the surroundings, and that's called exergonic, so very similar. And so when energy is exchanged between the system and the surroundings, it's either going to be exchanged as heat or work, or a little bit of both, some mixture. Those are the ways the energy is going to flow into or out of that system. So basically, the change in your E, change in your energy, is just heat plus work. Heat and work. And when you're talking about heat and work, and you're talking about whether they're positive or negative, it's really important just basically to stick with the convention that whenever we're talking about it, we're talking about the system. I mean, you could talk about it from the point of view of the surroundings and change the sign and mean the same thing, but that gets confusing. So whenever we talk about a change in a Q or a change in W or a change in E, we say if it becomes positive, it means the system is gaining heat. If it's negative, it means the system is losing heat. So we're always looking at it from the system's point of view because that makes the most sense. The system is the chemical reaction that we're trying to talk about. So similarly, again, terms you have heard before, if heat is being absorbed by the system from the surroundings, this is considered an endothermic reaction. So heat is going in. And when heat is being released by the system, this is an exothermic. Heat is exiting the reaction, basically, is exiting the system. Those are terms, again, you should be familiar with. The next thing we're going to talk about is a state function, because knowing if something is a state function can be pretty handy. A good example of this is figure out E. So usually we can't really know the internal energy of a system. It's basically too complex of a problem. But we don't really need to know the internal energy. I mean, we need to know, but we don't need to know how it got there, right? The internal energy is independent of the path by which the system achieved that state, right? So if we're looking at this system down here, we've got water that's at room temperature, right? We can figure out the E here, right? It doesn't really matter how much energy, we don't know if it started off at 100 degrees Celsius and cooled down, or if it started off at 0 degrees Celsius and warmed up. It still has the same E, all right? So we call that a state function. So it just depends only on the present state of the system, not the path by which the system arrived at that state. I like to think of it as like somebody climbing a mountain, right? Person A could just take the most direct path up, and person B might get lost and go left, right, up, down, and take this your circuitous route. They both start at the bottom and end at the top, right? It doesn't matter. They're both at the top. That's the state function. One guy walked a lot farther because he got lost, but it doesn't matter because he made it in the end. Q and W, heat and work, though, are not state functions. Okay, so you could have this battery here. You could short it out and lose all of your energy as heat. Right, so if you come here, your charge battery, you end with an end at a discharge battery, so the delta E, no matter what, is ending there, but you lost it all as heat, right? But if we're running the fan, yeah, we're going to get some heat too, but most of it's going to be done by work in turning the blades, right? So you have the same delta E no matter what, but these are going to be different. The path does matter in this case. If you've got less work, you're probably going to have more heat. If you have more heat, you're going to have less work. So that depends on, that is not a state function. That does depend upon the path. And so if you want to look at the enthalpy of an entire reaction, the delta H is just going to be the products minus the reactants, right? Basically the same thing as final minus initial for your delta E. Same idea. And so this is called the enthalpy of reaction, or sometimes called the heat of reaction, because they're basically synonymous. And so things just to keep in mind about enthalpy, it's an extensive property, right? So it does matter, amounts do matter. Delta H for the reaction in the forward direction is the same size but opposite direction for the reverse reaction. So depending on how you write it, if you want to reverse it, that's fine. The delta H stays the same. It would just, if it were positive in the one direction, it'll be negative in the other direction. And it does depend upon the state of the products and the state of the reactants. So if you have to look up delta H values, you have to make sure you're looking up, delta H for water if it's liquid, gas, or solid. So it does depend upon the state. So an example, given the thermochemical equation, this right here, we've got your delta H, right? You want to figure out how much heat is evolved if you have 74.6 grams of SO2. We're converting it to SO3. And so basically we just need to convert our SO2. We've got 74.6 grams. We're going to convert that to moles because that's the useful unit. And then since they're equimolar, it's also going to be the moles of SO3. And you know that you're doing you're losing 99.1 kilojoules per mole of SO2. So overall, you would be creating, you'd be creating 115.5 kilojoules would be exiting the system. So we talked about well, I hinted a little bit at calorimetry. Since you can't really, before I kind of hinted at this, since we don't know the exact enthalpy of the reactants and products, we can measure the delta H, the change, through calorimetry because it's an open system, so we can just measure the flow of heat. So the way this works is you've got some kind of reaction that's taking place in an aqueous solution. And so in this case, this reaction mixture, the water, is actually part of not the system, but part of the surroundings. And so you can see as energy flows from the molecules that are reacting into this water, you can measure the change in temperature. And you're an insulated environment. You know, it's kind of funny, but 2 styrofoam cups nested together with a top on it is actually really good. And so that really any change that happens in the temperature of this water is, you know, the vast majority is going to be due just to the chemical reaction that's going on within the cup, within the calorimeter. So one thing you need to talk about when you're doing calorimetry is heat capacity, or sometimes called the specific heat. And that's just the amount of energy required to raise the temperature of a substance by 1 degree. So that's its heat capacity. So again, sometimes called specific heat. Water actually has a quite high specific heat. That's one of the kind of cool things about water, is it has such a high specific heat. It takes a lot of energy to change the temperature of that water. If you're looking at the actual specific heat, or specific heat capacity, it's basically the same thing, except now we're being specific in the amount that we have. So this is 1 gram of a substance by 1 degree C, or 1 Kelvin. And you see here, right, the specific heat of water is 4.184 joules, which we also call a calorie, right? And that's where a calorie comes from. A calorie is defined as the amount of energy it takes to raise 1 gram of water 1 degree Celsius. So that's why those are the same, not just a big coincidence. So specific heat then equals the heat transferred over the mass of whatever it is that's transferring heat times the temperature change. So super useful equation right here. So specific heat is the heat transferred over the mass times the delta T. So let's look at an example of this. How much heat is needed to warm 250 grams of water from 22 C to 98 C? And the specific heat of water, like we just said, is 4.18 joules per gram Kelvin. So how do you do this? All right, so this is the equation you're going to be using. And we can, since we're interested in heat, we can rewrite it to solve for heat, solve for our Q. And we have our specific heat of water. We have our mass, 250 grams. We just got to figure out what our delta T is. 98 minus 22, 76 degrees C. So just plug everything in and solve for it. And so the amount of heat needed to raise that much water, that temperature, is 7.9 times 10 to the 4th joules. And so again, if we're carrying it out in this calorimeter, really if we want to figure out the heat of the reaction, it's just the opposite of the heat of the solution, right? Because any energy that the reaction loses, the solution is going to gain. So Q of the solution is the opposite of the Q of the reaction. And so since we know, like I said, the specific heat of water, we've documented that lots and lots of times. The delta H for the reaction then is just the Q for this reaction. So Q equals delta H. So here's another example for us. So a student mixes 50 mils of 1.0 molar hydrochloric acid with 50 mils of 1.0 molar sodium hydroxide in a constant pressure calorimeter. The temperature of the resultant solution increases from 21 to 27.5 degrees C. So we want to know the enthalpy change for the reaction in kilojoules per mole of HCl. We're going to assume negligible heat transfer for the calorimeter, which is going to be the case for all your questions. The total volume of the solution is 100 mils. Its density is 1.0 grams per mil, and specific is 4.18. Okay, so we were given 100 mils of water, and a quick conversion, 1 gram per mil, so we have 100 grams of water. And our change in temperature was 6.5 K. And so we just use our calorimetry equation, where the heat of the reaction, Q reaction, is the opposite, or the negative of our specific heat of water times the mass times the change in temperature. So we just plug our values in. We have our specific heat of water, we have 100 grams of water, we have our delta T, So we have negative 2.7 times 10 to the third joules. But we were asked to find in kilojoules of mole per HCl. So we have negative 2.7 kilojoules, and we had 1 molar HCl times 0.05 liters, so we have 0.5 moles of HCl. So then negative 2.7 kilojoules per 0.05 moles is negative 54 kilojoules per mole. So similar to this, a little bit different. You could also do something called, you could do these reactions in a calorimeter called a bomb calorimeter. And we call it bomb because it's sealed, right? So if you had built up enough pressure, obviously it could explode. But same idea. In this case, so the heat absorbed or released by the water is still a good approximation for the enthalpy change for this reaction. All right. But because the volume in the bomb calorimeter is constant, all right, so what's really being measured is going to be a change in delta E, not delta H, right? So we can't just say that heat is delta H before, because now we're not in a constant pressure. It's sealed, and so the pressure can be changing, so we can't make that assumption. So for most reactions, it really isn't a huge difference, so you don't have to worry about it too much. So in this case, the Q of the reaction is going to be the opposite of the specific heat of the calorimeter times delta T. So an example of this. So combustion of methyl hydrazine, CH6N2 in a liquid rocket fuel combusts as follows. All right, and so 4 grams of methyl hydrazine is combusted in a bomb calorimeter. The temperature of the calorimeter goes from 25 to 39.5. And then in a separate experiment, we figured out that the heat capacity of the calorimeter is 7.794 kilojoules per degree Celsius. Calculate the heat of reaction for the combustion of 1 mole of methyl hydrazine. Okay, so we've got our delta T. That was easy. So the heat of our reaction, the Q of our reaction, is just the opposite of our the specific heat of our calorimeter, or the heat capacity of our calorimeter, and our delta T. So there's our heat capacity, there's our delta T, so negative 113.0 kilojoules. And again, they asked for us for per mole of our substance. So we had 4 grams of our substance, and we convert that to moles. And so you have negative 130 times 10 to the third kilojoules per mole of our methyl hydrazine. All right, last thing we're going to talk about, Hess's law, and a different way to figure out the delta H of your whole reaction. So we know the delta H for lots of reactions already, and it's not really all that convenient to measure delta H for every reaction that we're interested in, because people have done it lots, and it doesn't really change. So there's an easier way to go about doing this when you need to. So we can estimate our delta H using our published delta H values. Okay. And so basically, Hess's law states that if the reaction is carried out in a series of steps, delta H for the overall reaction is equal to the sum of the enthalpy changes of the individual steps. All right, so our overall enthalpy is the same, right? Going from here to here is the same as if we go in our steps, right? We're going to end up with the same spot. And so if you know the steps, you can figure it out, or if you know enthalpy of different parts of the steps, you can figure it out. So again, delta H is a state function, so the total enthalpy change depends only on the initial state of the reactants and the final state of the products. All right, so an example. Calculate the change in enthalpy for this reaction. So we got 2C plus H2 equals C2H2. And we have the following equations and their enthalpy values. So we can use these in Hess's law to figure out our delta H for this reaction. So even though we don't have our delta H for this reaction, we've got all these component reactions that we can use. So how do we do that? So the first equation has our product as a reactant. So we said before, if we reverse the reaction, it's equal in magnitude, but just different sign. So we just turn it around in opposite sign. So we just switch that first reaction around. So we've got 2CO2 plus H2O yields. Hey, there's our product. Woohoo! We just added a plus sign in front of our delta H that we had before. We need 2C as well. Our second equation had only one C, so we're going to multiply equation 2 by 2. All right, so we do that, and we just do the same thing with our delta H value. We multiply that by 2. And then we still need H2 as a reactant. Equation 3 has H3 as a reactant. It has the amount that we need. We don't have to do anything to it. Okay, so now we can just take these, add them all up, and there's our delta H value for the reaction that we actually care about, 226.8 kilojoules. If you're talking about the enthalpy of formation, so it's the enthalpy change for the reaction when a compound is actually made from its constituent elements. So that'll be delta HF for formation, constituent elements from their elemental forms. And we often talk about standard enthalpies of formation. Standard is denoted with this superscript 0. So this is the change in the standard enthalpy of formation. These are things that are measured under standard conditions, which is 25 degrees C, 1 atmosphere pressure, and usually talk about 1 mole of reactant. So what do we do with this? Again, we can think of this reaction. So if we're trying to calculate delta H of this reaction, okay, you can think of it as happening in lots of different steps, right? The C3H8 can decompose into graphite, right? And we have a value for that. That graphite, then we can combine it with some oxygen and get some carbon dioxide. So here we have formation of carbon dioxide. We've got that H value. And then you can add your hydrogen and your oxygen to create some water. Right? So all those things are happening. We've got that value here too. All those things are happening in this overall reaction. Right? So we add those 3 reactions together, and we get the reaction that we're actually looking for, and then we can also add together their delta H values and figure everything out that way. So we can use Hess's law basically like this, right? So the delta H is just going to be the sum of your delta H's of your products times the stoichiometric coefficient minus the sum of the delta H values of the reactants times their stoichiometric coefficients. So if we're looking at this guy here, you've got your different amounts. So our delta H, we've got the sum of our delta H for our CO2 is negative 393 times 3 of those guys, and then negative 285 to make a mole of water multiplied by 4, because we have 4 of those. So we're going to take that quantity, right? That's our products, and we're going to take away our reactants from that. And so we've got negative 103.85, right? The decomposition of this guy here, and then 5 times 0 joules for this. You don't have to worry about something that's in its elemental form, right? It's already its standard form. So something like that you don't have to worry about, because O2 is its most basic form. And so we put all those together, and we can get our total delta H value, negative 2219.9 kilojoules. All right, so one more example for you to try. You can try this on your own if you want, and pause, or just watch me, whatever works for you. So we want to find the standard enthalpy for the formation of your calcium carbonate. We have this reaction, and we know the standard enthalpy change for the whole reaction. So we have that part already. So similar to what we were just looking at, but basically looking for different values. Right? So your delta H, or your standard delta H for your reaction is going to equal the delta H of formation of your calcium oxide times 1 plus your CO2 times 1 minus your reactants calcium carbonate times 1. And so you can just look those values up for the calcium carbonate, CO2. They're in the back of your book in the glossary or the appendix. We were given this for the whole reaction. The only thing we don't have is our calcium carbonate, so we can just solve for our delta H of our calcium carbonate. So the heat of formation of calcium carbonate is negative 1207.1 kilojoules per mole. And that is that for this set of notes. Next time we'll talk more about some more thermodynamic stuff, enthalpy and free energy.